Something huge is happening in the cosmos. Something our most trusted theories, like the Big Bang, never saw coming. The James Webb Space Telescope has just uncovered a cosmic treasure trove, over 30,000 ancient galaxies that simply shouldn't exist. Among them is a mammoth cosmic disk, nicknamed the Big Wheel, that was already fully formed less than 2 billion years after the universe began. These galaxies are too big, too orderly, and they showed up way too early to the cosmic party. As if that wasn't enough, new evidence hints that dark energy, the mysterious force tearing the universe apart, might be changing over time. And to top it all off, our best measurements for how fast the universe is expanding simply don't agree. Are we on the brink of rewriting the origin story of everything? The stakes have never been higher, and what we discover next could shape the very foundations of cosmology. Let's zoom in on one of these cosmic puzzles. It's a single galaxy, spotted by Webb, that has become the poster child for this entire mystery. Astronomers call it the Big Wheel, and its light began traveling towards us over 12 billion years ago. But what we see now is a fully formed galactic disk, spinning with the grace of a modern superspiral. The numbers are staggering. The Big Wheel is about 3 times wider than our own Milky Way was at the same age. It's as massive as our galaxy, but it got that big less than 2 billion years after the Big Bang. Even more shocking is its rotation speed. It's spinning as fast as the most mature spiral galaxies we see today, suggesting a stable, well-organized structure in an era where chaos was supposed to reign. According to our standard cosmological models, galaxies from this time should have been small, clumpy, and still crashing into each other. Yet, the Big Wheel's disk is smooth and orderly, its spiral arms already beautifully defined. The odds of finding a galaxy like this so early were thought to be less than 2%. But there it is, undeniable, immense, and spinning. The Big Wheel directly contradicts the slow, steady timeline predicted by the standard model. It forces us to ask, if one such galaxy exists, how many more are out there? And what does its very existence tell us about the rules that have governed the cosmos since the dawn of time? Recently, astronomers used the James Webb Space Telescope to conduct one of the biggest surveys of the early universe ever. In just its first year, Webb's deep field images revealed over 30,000 candidate galaxies, whose light began its journey less than 1 billion years after the Big Bang. These numbers completely dwarf what our leading cosmological models had predicted. According to the ΛCDM theory, our standard model, the early universe should have produced far fewer bright, well-formed galaxies in that period. Simulations based on this model predicted we'd find only a handful of massive galaxies from that early time. Instead, Webb's census reveals a sky teeming with mature systems, each blazing with hundreds of millions or even billions of stars. And the problem isn't just the sheer number of them. When modelers crunched the numbers, they found that the star formation efficiency required to create these galaxies is off the charts. For so many bright galaxies to exist so early, they must have been converting their gas into stars at a rate 2 to 3 times higher than what standard theory says is possible. In our local universe, only about 10 to 20% of available gas becomes stars. But the early universe, as seen by Webb, seems to demand efficiencies of 30, 40, or even 50%. This isn't just a few oddballs. The trend holds true across the entire population. It's not just one big wheel anymore. It's a whole generation of massive, well-formed galaxies appearing billions of years ahead of schedule. The numbers force a simple question. If our models can't keep up with the data, is it time to rethink the fundamental rules of the early cosmos? And the plot thickens. The latest results from the Dark Energy Spectroscopic Instrument, or DESI, have put dark energy directly in the spotlight. By creating the largest 3D map of the cosmos ever, DESI analyzed nearly 15 million galaxies and quasars. What they found was subtle, but the implications are enormous. The ESI's data suggests that the strength of dark energy might not be constant, as the standard model assumes. Instead, the numbers hint that it might be weakening over time, with statistical confidence reaching 4 sigma. That's pretty significant. This would mean the force pushing the universe apart isn't a static property of space, but a dynamic one that evolves as the universe ages. This possibility will completely upend the ΛCDM model, which has been the bedrock of cosmology for decades. For years, scientists have relied on this constant to explain everything from the afterglow of the Big Bang to the large-scale structure of galaxies. But JWST evidence points to a universe where the rules themselves might be changing right under our feet. So, if dark energy is changing, what does that mean for our measurements of the universe's expansion? This brings us to one of the biggest headaches in modern cosmology, the Hubble tension. For 2 decades, we thought we had the universe's expansion rate figured out. But today, 2 numbers stand in stark opposition. On one side, we have 67 kilometers per second per megaparsec, a value calculated from the afterglow of the Big Bang. On the other, we have 73, a number measured from nearby galaxies. That's an 8% difference, and it's far too big to be a simple mistake, especially now that the James Webb Space Telescope has weighed in. Nobel laureate Adam Rees and his team used Webb's incredibly sharp vision to recalibrate their measurements of local galaxies. The result? A Hubble constant of 73.5, with an error margin of less than 2%. This confirms their previous findings with unprecedented precision, meaning simple errors can no longer explain the gap. Every galaxy, every supernova cross-check points to the same conclusion. The universe around us today is expanding faster than our models of the early universe predict. The 2 values just refuse to meet in the middle. With JWST's confirmation, this mismatch is now baked into the data. It's no longer a statistical fluke. This leaves us with a profound dilemma. Either something fundamental is missing from our standard model, or the universe behaves differently than we've ever imagined. This is where fascinating new ideas come into play. Take David Wiltshire's Timescape Cosmology. It proposes that the universe's patchy structure full of dense galaxy clusters and vast, empty voids actually affects the flow of time itself. In this model, time doesn't tick at the same rate everywhere. In a dense region like our galactic neighborhood, gravity is so strong that clocks run measurably slower compared to those in the empty voids between galaxies. In fact, a clock inside a galaxy could lag behind one in a cosmic void by as much as 35% over the universe's lifetime. That means billions more years could have passed for an observer in an empty region than for us here. When researchers analyzed supernova data without assuming a uniform cosmic clock, they found strong statistical support for this timescape idea. In this view, what we perceive as dark energy might just be an illusion created by the way time stretches and contracts across the cosmic web. The universe's apparent acceleration could just be the result of us living in a slow-ticking corner of the cosmos. But wait, there's one more twist. A strange new pattern has emerged from the data on early galaxies. They don't spin randomly. Out of hundreds measured, about 2/3 spin clockwise, while only 1/3 spin counterclockwise. That's a 66 to 33% split, far too skewed to be random chance. This isn't just a local fluke. It hints at a cosmic scale preference, as if the universe itself remembers which way it was spinning from the very beginning. Some theorists propose this could be the fingerprint of our universe's birth. What if our cosmos was born inside a rotating black hole? The initial spin would imprint a preferred direction on everything that formed within it. In this radical view, the spiral patterns of ancient galaxies aren't random at all. They are echoes of a primordial rotation. This is a wild idea, but the data demands an explanation. From galaxies appearing too early to a changing dark energy and a cosmic expansion rate we can't agree on, our standard model is facing its greatest challenge yet. Alternative ideas like Timescape Cosmology or a spinning universe highlight just how many questions remain. As more data streams in from the James Webb Space Telescope, the debate over the Big Bang model is being driven by hard evidence, not just speculation. One thing is clear: the universe is far more complex and surprising than any single theory can explain. Thank you so much for joining me on this journey to the edge of cosmic understanding. If you found this as mind-blowing as I did, please hit that like button, subscribe, and ring the bell so you don't miss our next deep dive into the mysteries of the universe. See you next time.